Welcome to another tutorial video on using the SkyX. In this particular one I'm going to look at doing periodic error correction and how to do a T-point model. My telescope is a standard refractor with a focal length of 650mm, and if I just sat the telescope on its losmandy plate on the desk, the small guide camera that I've stuffed up the focus tube is in a portrait orientation, so the long axis of the sensor is pointing vertically upwards. What you're going to do is take a sequence of pictures as if you were auto-guiding, but in this particular case you're going to turn off the auto-guiding commands themselves, and the SkyX will produce a log file that will then be interpreted by its utility to create a periodic error correction file. Before we get started, there are a number of different setups that we need to just confirm. If we go into the Telescope tab and Tools and PEC TCS, we need to go into the Periodic Error Correction tab, and we need to make sure that there isn't anything there. So we need to just make sure that Apply PEC is disabled, and that means any prior correction is now not in operation. The other thing we need to do is in the Telescope tab up here, T-point add-on, is make sure that T-point is turned off and also that ProTrack is also turned off, again, so there's no other interruptions. Before we get started, you should focus the camera using the focus tools that you're most comfortable with, and you also need to know what the image scale is in arcseconds per pixel. To do this, if I go onto my auto-guider tab and simply take a photograph of about 4 seconds or so, I will get an image on screen. And there's a few dots of stars there which should be sufficient, but you can't directly do an astrometric solve, you have to save it as a file first. So I just do save as, and I've got a temporary file on the desktop, and I'm going to replace it, and then I'm going to do photo to image link. I know roughly what the scale is, it's about 0.8. So there's something approximation 0.8 there, and I put down unknown image scale, and I'm going to click find astrometric solution. And it's found it. And the key number here is the one just highlighted here, 0.761 arcseconds per pixel. And we will need that later on when we come to do the PEC calculation. So I can close that for the moment. I can also right click on this and remove the photo to get it out the way, and I can zoom out. Now, for some reason it always defaults to what they call the celestial sphere, so I'm going to do terrestrial sphere, which is far more convenient. So this is my view of Earth, as it were, or view of the sky, and my imaging horizon in orange. And what I'm going to do is I'm going to slew to a star that's close to the meridian and at 0 declination. So this line here is 0 declination. And if I just slew to a simple star just to the west side of the meridian. So just take a few seconds, and I'm going to simply take a picture. The reason that you do it at 0 declination is so that the calibrated error value that the autoguider works out is accurate. As you increase declination, then it starts to shrink what the error is, and it creates a false value. So at 45 degrees you get the cos of 45 degrees, which is 0.7, so your corrections are out by a factor of 0.7. So let's just simply take a picture, and let's see if we can find a star that's suitable for guiding. And what we're looking for is a star that's not too dim or too bright, but just right. In other words, the Goldilocks one. And there appears to be one there. So I'm just going to do a subframe and draw a subframe around there. And I'm going to take another picture. Now this is with a 4-second exposure, which is potentially a little bit on the long side. If I put my cursor in the middle there, it has a peak value of about 24,000. So I think I can afford to drop that down to 0.5 seconds and just simply take another picture. The reason being is that you want to be fairly quick. Although you'll get seeing conditions, which will obviously average out with a very long exposure, the problem is that if you have a fast changing tracking error, so you really want to be responsive, and that's why I'm using a guide camera, which is typically a smaller chip and much faster response. So now what I'm going to do is I'm going to go into the auto guide settings. So if I go to the auto guide tab here and do setup, I need to make sure that the relays are disabled. These little boxes here are the enablers for each of the axes on the autoguider, and then all need to be turned off, which they are. Now what I need to do is double click the guide star. So I'm going to click on that, and the coordinates are put in here. And then lastly, I need to log the auto guiding but clear the log. So I'm going to click on this button here, and it's now cleared. I'm going to bin one by one to give maximum accuracy. I don't need an exposure delay because I'm not correcting anything, and I can now hit auto guide. And it will quickly take pictures of the stars every half a second, and it's going to log the position of the star and the error value over the next 15 plus minutes. If you look in the instructions, each of the Paramounts have a different cycle time for their worm, and they recommend a minimum of 4 worm cycles. I'm going to let this run for about half an hour because that gives me the most worm cycles. It also helps if you have accurately polar aligned your mount, since it means that the overall drift rate on the star over this period is going to be good. So I'm going to pause the video here, and I'm going to rejoin it when I'm close to the end of my calibration run. Welcome back. You rejoined me about 25 minutes after starting the guide log. Just a couple of the things I realised I hadn't explained. The default track box size is, I think, 67 by 67 or somewhere around there. In case you've got a bit of drift on your guide star, it's a good idea to increase the size of the track box, and you can do that by clicking this button and choosing a different setting. I've chosen 200 by 200. That gives me a nice quick area, and it's unlikely to be lost in that space. As you can see on the screen, that the star has basically not moved from the centre, which is a good sign. So in a couple of minutes I'm going to stop the autoguider and then open up the system that calculates the periodic error. And just to show you where the file's being stored, if I bring up the Finder, it's under Documents, Software BISC, the SkyX Professional, and it's sitting under Camera Autosave. And then under Autoguider, December 27, and there's my log file that's being still sort of written to. So I'm just going to remember that. I think by default when you load up the log file it goes to this folder anyway, but in case it doesn't, that's how you find it. It's within the Documents, Software BISC, SkyX Professional, Camera Autosave, Autoguider, and then today's date. So let's bring this to a close, and I'm just going to hit the Abort tab, and I'm now going to go into the Telescope tab, Tools, BISC TCS, and Periodic Error Correction, and I'm going to do this tab down here called the Compute PEC Curve. So what I first of all need to do is put in my image scale. So 0.761 was my imaging scale, so it's got 0.76. I think it only does 2 decimal places here. And it says here, data was collected when telescope was pointing west. I need to select that because if you look at my system here, it was on the west side of the meridian. and there was no meridian flip or anything like that to worry about. I'm going to check all these boxes, and I'm going to open the tracking log, and so I need to go back up one level to December 27th, my autoguider log, and I need to compute it. So before I do that, I need to make sure that the mount is selected correctly. This is a Paramount MX, and I do fit. So when you look here, you can see there's the periodic error that it thinks is there, and if I uncheck that, you can see the raw data, then the curve fit that's tracking that data, which looks like quite a good curve fit. It looks pretty accurate. There's a couple of times when it seems to be higher and lower, but generally speaking that looks like a good fit, and it's between 1.4 and minus 1.2 arc seconds. So 2.6 arc seconds peak to peak, which is an extremely good value. And then the actual curve, the error curve, which is computed. So now what I need to do is do save to mount. And then if I hit the PEC TCS table, there's the worm gear moving along, and this is the curve. And if I do apply PEC up there, it is now applying it, and there's nothing more for me to have to do. Let's take a look at TPoint. So I'm going to close this down, and I'm going to bring my telescope mount to point to somewhere near the top. And while it's doing that, I'm going to bring up a few extra little tabs where we need to just check a few things off. Now in this particular example, I'm using my guide camera as an imaging camera to work out the astrometry, but typically this would be your normal imaging camera, and it is better to use an imaging camera because it'll be slightly heavier, there'll be a little bit more flexure on the focusing tube, and so forth. A couple of things to check first. One is the time. So I have a little utility called Dimension 4, which is a free utility, and it synchronizes your computer with the internet. And you can see that it's adjusted it by 1/3 of a second. I'm going to do it again, and until it stops making big changes. So 0.01, 0.12. That's probably good enough. It sometimes takes a little while for it to settle in. I can now shut that down. No longer need it. So I know that my right ascension should be as accurate as it can be. The other thing I need to do is check the atmospheric conditions. So on my telescope tab, if I do telescope setup and atmospheric refraction parameters here, it's assuming the temperature that you can measure inside the mount. There's actually a temperature sensor sitting inside the mount, and it's got some numbers that were the last numbers I plugged in for the pressure. So if I just check out what the pressure is, it's 972 is the pressure, and it's 87 humidity. So I'm going to, and 972. And then I'm going to hit OK. The temperature, if I alter the temperature here, I can override it, and then it won't track. So I'm just going to leave it as it is. And I'm going to close that. And we already know the scale of the camera, which is useful. We're going to need that. And in the telescope tab, there's TPoint add-on. And I hit the setup tab, and I'm going to hit this tab here, which is add-on settings, and do new. I'm going to clear it all, and then I'm going to hit the calibration run and hit start. And there's your atmospheric conditions that came up previously, so that's good. I forgot that did that. And on my autoguider tab, I need to disconnect it, and on my camera tab, I need to connect it. There's no temperature control, so now my guide camera is being used as the imaging camera. So if I go back to this tab and automatic calibration, what I need to do is get the scale right. So what I can do is to simply take a picture and do auto scale. And it says 1.52, and the reason it says 1.52 is because I'm binning the exposure. So I'm going to say yes to that, and I'm binning 2 by 2. This does two things. It reduces the download time and speeds up the plate solve. And it's not, because these are small pixels on this camera, I do not need 1 by 1 binning. So that's absolutely fine. Exposure time is short. I'm binning 2 by 2, so it should be quite rapid to determine the scale, do the astrometric plate solve, and move on. So having done all that, I can now, under automatic calibration, create pointing targets. So this slider along the bottom here changes the number of targets that it's doing, and you can either have them regular or random. I prefer to have random, and there are a number of settings on here that I'm just going to enlarge this to show you what they do. So these settings set a dead zone which it doesn't try to calibrate within, and that's typically within a few degrees of the northerly meridian. So I've got start of 2 degrees and finish of 358, which is absolutely fine. This is a refractor, so I'm quite good at getting quite close to the zenith. It's on a pier, so this is within a few degrees of the zenith. And then the altitude start, which is this one, I'm going to stick it at about 35 degrees, something around there. Some of these points will clip because my imaging horizon can go up to about 42 degrees in some directions. So I've clicked this box, clip at horizon. I don't need to sort for a dome because I'm using a roll-off roof. And I'm going to increase the number of targets until I have a couple of hundred or so. So there's a couple of hundred, 219. If I now click on the last tab, which is acquire pointing samples, all I do is hit run. And it'll immediately start slewing to a target and start working it out. So 2-second exposure, plate solving, move on to the next, which is quite quick. So I can shrink that, I can shrink that, I can shrink that. So under chart elements, if I scroll down here, you can see telescope crosshairs, pointing sample, and so forth. So if I come back out of here, you can see all the samples it's going to do over the sky, and the solid ones are the ones that it's already completed. So it's already on to point 8. So again, I'm going to abandon you for about 3/4 of an hour probably, and I'm going to let it do its thing. To see how well it's doing, if you restore these windows, you can see how it's getting on in terms of the number of samples. This one will also show you the image, which one I'm looking at. Don't need that one anymore, and I need this one. So this one says that so far it's done 11 targets and they've all plate solved okay. So I can shrink that, and the other useful thing on here is the polar alignment tab. So as more samples get added, it shows you the average error that's going on, and it also tells you whether your polar alignment is off. At the moment it's on one side of the meridian, so it typically will get a slightly skewed result for the polar alignment. But once it's done the whole sky, these numbers normally get better and better. And then finally, we're going to be looking at the model tab here. So at the moment it's a very simple model with only 6 terms. But later on, with this number of points that I can look at, I'm going to be doing something called a supermodel. And that introduces automatically a whole number of other points in the algorithm. And that'll include things like flexure and so forth. So right now, there's not much I can do other than just to let it go and do its thing. So the run appears to have completed. If I click on here, get rid of the image and click on this one, we've got all our 219 samples done. As we'd expected, there's a few that it didn't like, mostly because there was a moon up and also my horizon was probably clipping in a few instances. So that's pretty good. Most of the images were successful, so I can just shut that window down. Look at the polar alignment tab. So at the moment it says tighten the right knob 0.4 ticks and raise the polar axis 1.1. So that's a pretty good alignment, and I'm not going to touch it at all. If it was anything more than that, potentially I might do that. And I'm not going to go into that here, but there is an advanced polar alignment routine within this program that once you have worked out an accurate polar assessment, it asks you to move to a star, and then it asks you to use the Alt-As commands to actually physically move the mount to line the star up. We're not going to do that right here, but I'll show you where it is. You can see that my RMS pointing error is only 37 arc seconds, which is a pretty exceptional result, and that's using a model with only 6 elements. If I hit the supermodel, it'll start working out a far more complicated model of all the errors in the system, and hopefully that number will come down quite significantly. In regard to the number of samples, if you are doing image acquisition and you're using a sync method of some sort, you don't really need a pointing model at all. It's really more of a convenience feature here. So what I've just done is run the supermodel, and it's now saying that with the supermodel it can reduce the RMS pointing error to 3.7 arc seconds on average, which is just over 2 pixels, which is an exceptional result. So I'm going to hit apply, and now that is put over here, and you can see all these models have suddenly been populated with all different sorts of things about flexure and non-orthogonality and so forth. Hit on the polar alignment tab, and now we're talking about 0.5 ticks and 0.3 ticks. So basically my polar alignment is excellent. Now in terms of what to do next, if you look at the setup tab, pointing corrections is ticked, and if you look at the ProTrack tab, I can now activate it and enable it. If you'd only done maybe a dozen samples, you can't really run ProTrack. You need to have a significant number of samples in order to do that. And let me explain the reason why. If I expand this out and then change this to multiple graphs, these are all the different types of analysis that the program is working out. And sometimes you see a distinct pattern where, depending on a particular setting, you get a particular type of error. And it's characterizing the mount in terms of a number of different mechanical attributes. So I can close that for the moment, and what I'm going to do is just see if it works in practice. So if I zoom out, say, again, move my terrestrial sphere, which makes life a lot easier. So if I go to Capella, slew 2, so I'm now slewing to Capella, and we'll just see how accurate it is. It's slewing quite slowly today because it's cold weather and I've reduced the slew speed in cold weather. Camera tab, take picture. It won't need very long because it's a bright star. And if I hit the crosshairs, that I think is proof of the pudding. Thank you for watching. Just before I leave you, I'll just show you where the advanced polar alignment is. So under TPoint add-on, if I pull that back to there, change it back to scatter plot, and polar alignment at the bottom here, I think it's here, is accurate polar alignment, and that will step you through a process whereby it takes an image of a star, it'll automatically offset it, you then tweak it so it's deliberately right, and you have a brilliant model that is perfectly polar aligned. Anyway, I'll leave that there, and just for information, if you have multiple setups and you want to store these setups and they're fairly repeatable, under the setup tab there are a number of other options where you can import and export data and save it for later use. But as I said at the very beginning, I'm using a lighter weight guide camera to do this model. It's probably sufficient for the purposes I need, but if I wanted a very accurate model for imaging, I would use my proper imaging camera to take these images, because the weight of that on the focus tube and on the system will cause a little bit more flexure than the lightweight guided camera. So thanks for watching and have a good holiday.